Record. Okay, so join. Oh, yeah, continue. Okay, recording. All right, so let's say co-host. There you go. Here, I'll start my video for people on video. There we go. All right, so what do we want to do? We just want to keep going? Just keep going in order? Yeah, so we just did chapters 20, 23, 21. How do we feel about those new material? The new material feels good? Yeah. So do note that there's 2 practice final exams. They cover all of the chapters equally, but I also have extra practice problems for just chapter 20. So that's electrochem, because in typical years, chapter 20 had been on a midterm, and I want you guys have access to those practice questions as well. So just for you guys, it ends up being on the final. So midterm 1 covered solution chemistry, kinetics, and the intro to chemical equilibrium. So let's look at that. All right, benzene. What? Oh yeah, thanks. Oh yeah, you don't need to see me twice. Yes, thank you. Okay, got it. Go away. Okay. Am I still recording? Yes. Okay. All right. So, benzene, yes, was used as a common organic solvent for a long time, but it's a carcinogen. It causes like reproductive failure in both men and women. So what substance is predicted to be miscible with benzene? So miscible, oh, things are different now. Things are different. Okay. Miscible means, oh, they're so stupid. Okay. Wait, that's dumb. Before, my favorites bar had like highlighters and things on it. And now I have to click your top main color. I don't know. Yeah. Okay, so what's predicted to be miscible with benzene, meaning it mixes. So we want to look for IMFs that match. So based upon the chemical thing of benzene, and then how do I change the size? What? But oh, tap twice. Oh, okay, there it is. There, yeah. Okay. I switch between 3 and 4 sometimes. So okay. So based upon the chemical formula of benzene, what is the strongest IMF there? Just dispersion. So we are looking for something else where it can form strong London dispersion with benzene. But technically, don't all these substances have London dispersion? Technically, yeah. So should all of them mix with benzene? No. So what we see is only bromine will mix with benzene, because bromine, think about it, like you have a pure sample of bromine, it London dispersions with itself. Introduce it to some benzene solvent, that LDF, that dispersion is fairly weak, so it'll break, bromine will break its dispersions to form new dispersion with benzene. Versus something like water. Water's strongest IMF is hydrogen bonding, so it's not very likely hydrogen breaks its hydrogen bond to form weaker bonds with benzene. That's not super, that's not thermodynamically favorable, so that's what we don't see. Yeah. Yeah, it works. So that's kind of like the whole, and so the comment was nonpolar dissolves nonpolar, and that is the observation we see. We also see similar polar things dissolve polar things as well, and that's kind of the lazy way that biochemists or biologists say like dissolves like, and that's true. Like things that have matching IMFs do tend to dissolve one another. So like water and chloroform, which is like CHCl3, more likely to dissolve in one another than, okay, now how do I point at stuff? What? Okay, there we go. Yeah, all right. Oh my gosh. This wasn't like lecture. I'd be freaking out. So water and chloroform much more likely to mix with one another because they at least have common dipole together, but benzene does not. So water and benzene tend not to mix, but water and chloroform maybe a little bit more. But where our like dissolves like thing breaks down is actually between, how do I highlight stuff? Okay, this is stupid. Okay, water and sodium nitrate. Does salt dissolve in water? Yes, but why? Is it because they look like one another? No. It's they dissolve in one another because when they mix, they form strong ion dipoles, which is a new IMF that's formed just between salts dissolved in water. So salt dissolving water is not explained by the like dissolves like thing that biologists say. It's a little it works most of the time. It's just a little too simplified. Okay, so let's look at this one. Density stuff. So what's my trick with concentration? So all the concentration units that we've learned about, here's my trick, all right, for concentrations. We've learned about mole fraction. We've learned about percent mass. We've learned about molality, which is equal to moles of solute over kilograms of solvent. So all of these things, these concentration units, they are related to one another. You can convert between any of them as long as you know the molar masses of your solute and your solvent. As long as you know those things, you can convert mole fraction to percent mass, mole fraction to molality, no problem, right? Where things get iffy is with molarity. And what do I like to say? Molarity lives on its own island, where the unit of molarity is moles of solute over liters of solution. And so if you want to move between these two islands, you have to know, you need to know density. Density of your solution, grams per milliliter. That's what allows us to go from the kilogram mole realm of things to the liter realm that is in your denominator. So the important thing in this denominator, what students often forget, is liters of solution. It's the volume of both the solute and the solvent together. Versus in molality, it's kilograms of solvent, so it's just the mass of just the solvent. So those are some details there. So all of these you can interconvert perfectly without density, but in order to get to molarity, you do need density. Also, to go from molarity to any of these things, you need density, right? So to go between the islands, you gotta have density. So we wanna convert a molarity amount to molality. So do we need density? Yes, we do, and we are given density. So I always like to look at the unit given and think about what is the unit of the thing I want. So I'm given molarity. So this value means moles per liter. So for every 0.872 moles of my solute, so in this case it's K2CrO4, I have 1 liter of solution. That's what that unit means. I want it in molality, so the units I'm looking for is moles of solute, again, so K2CrO4 over kilograms of solvent. What is the solvent here? What is usually the solvent? Water, yeah, so it's not, we didn't have to assume it's water. We know it's water because it says aqueous. So since it says aqueous, it does mean that water is the solvent. Okay. So I need a mole amount of solute, and I need a kilogram amount of my solvent. So let's do the easy one first. Is there one I already know? Yes. I already know the top numerator part, moles of our solute. So I already know that top number. I just need to figure out how many kilograms of solvent I have, because the assumption that I'm working with right now is that I have 0.872 moles of solute and I have 1 liter of solution. I have both of those at the same time. And so we already used this top bit, so now we're going to use this bottom bit to figure out how many kilograms of solvent I have. So I have 1 liter of solution, so that's 100 milliliters of solution. So this is where density comes into play. So there's my density, okay, which means 1.129 grams of my solution is equal to 1 milliliter of my solution. Milliliter is the same as a centimeter cubed, all right? And so with that information, I'm able to convert the volume amount to a mass amount of solution. So 1 milliliter is 1.129 grams. So therefore, I have 1.129 grams of solution. Great. Is this the number I put in the denominator? No. What do I have to do? You'd think kilograms. So once I convert this to kilograms, so what is that in kilograms? 1.129 kilograms. Is that what goes in my denominator? No, it's not, because it's kilograms of what? Solution. What needs to go in the denominator? Solvent. Yeah. So remember, solution means solute and solvent. So I just want the solvent bit. All right, I just want the solvent bit. So if I know how much this whole thing weighs, solute and solvent. How can I figure out how much my solute weighs? From the mole amount. So this is the common mistake. Students will oftentimes put this number in the denominator and think they're done. They'll think, oh yes, solvent, solution, same thing. Nope, not the same thing. So I need to figure out how much my solute weighs. So I'm going to use the 0.872 moles of my solute, K2CrO4, and I'm going to figure out how much that weighs, right? Because that's, I have both of those things in my solution. So 1 mole of that weighs 194.19 grams, and then that equals something else. Yes, okay, so that weighs 163 grams, no, that's not right, 169.3 grams of solute. So together, all this information right there allows me to figure out that the gram amount of my solvent, I have 959.7 grams of water present, and that is what goes in my denominator, well, in kilograms, right? So finishing this up, finishing this up to calculate molality. What is this? Oh no, what did I do? Oh, my back buttons, like they swapped places. Can I move you? No, I can't. Great. Okay, so what am I doing? I'm calculating molality. Molality is moles of my solute, which I already have, over kilograms of H2O, my solvent. So the answer is 0.872 moles over 0.9597 kilograms of water. And so this is the step, this, converting the gram amount of your solute to figure out how much of your solution is your solvent. That's the common mistake students do. All right, and so that answer, I don't know, is 0.909 molality. All right, and so that's the harder one. Using where you have to use density. Okay, and oftentimes with these concentration unit questions, it's always, how do I start? That's often the hardest thing. So let's just kind of work our way through problems. like, okay, pretend I have sodium chloride and water, salt water, okay? Salt has a molar mass of like 54, I think, grams per mole, and water is like 18 grams per mole. Okay, so if I have something that, a solution where its mole fraction of NaCl is 0.21, how do you think you would start? You need to start with something. What is the easiest thing to start with, to start off a concentration unit conversion, if you're given mole fraction? Yeah, you're assuming something, yes. So you said assume 100 grams. Does it make sense to assume grams when this is mole fraction? Assume 1 mole. Assume you have 1 mole of stuff, 1 mole of solution. If you assume you have 1 mole of solution, how many moles of NaCl do you have? 0.21 moles of NaCl. Does that tell you how many moles of water you have? Yes, you have 0.79 moles of water. Right? That's where you start. So if you're given mole fraction, assume you have 1 mole of solution. That fraction becomes mole amounts. So hopefully you can see, if I wanted mass percent, right? Mass percent is your mass of NaCl over your mass of solution. Do you see via the units how you would get this? How would you get mass of NaCl? You just convert the mole amount to mass. Then how do you get mass of your solution? Is it the mass of this water? It's the mass of both of them added together, right? So basically you just need to convert both these mole amounts to gram amounts. You do mass of NaCl over mass of NaCl plus the other one. Well, what if I asked you to do molality with these same things? The molality of this would be equal to moles of NaCl over kilograms of your solvent, so H2O. Do you see the pathway to get from our starting assumption to molality? We actually already have the numerator. We already have moles of NaCl. How would we get the denominator? Kilograms. You just convert this to grams, then to kilograms. The water, that's it. So see how we have not had to use density yet. We didn't need to use density yet. Okay. So that's if it was mole fraction. If I gave you mass percent, let's say I said, oh, okay, you had 16% NaCl by mass. What's the assumption you want to start with? You have 100 grams of solution. So if you have 100 grams of solution, that means that you start with 16 grams of NaCl, and then that also means you can figure out how much water you have. I think I can do that math. I think it's 84 grams, yeah. And so since you know the identity of the things, salt and water, those gram amounts you can convert to mole amounts, right? And then the same ideas here, that you would simply, using the molar masses, be able to convert to molality or even mole fraction if you wanted to, the same reason, or with the same reasoning, right? Okay, and the last one, just to be complete here, if I told you that you have a solution that is 0.50 molality NaCl, what does that mean? You have a solution that is composed of 0.5 moles of NaCl. And what else do you have? 1 kilogram of, not solution, solute, which in this case is water, H2O, right? And so because you know the mass of H2O and the molar mass, you can convert You can convert this to mole amounts. You can convert this to mole fraction. All right. You can convert the mole amount of NaCl to grams of NaCl. That's how you get to percent mass. And that's how and so the hardest part is getting started. Getting started. So there's only, I guess, 3 you need to know. Mole fraction, percent mass, and molality. And I guess molarity too. All right. And that's the hardest part, knowing how to start. But it's all about, okay, are the mole amounts of solute and solvent additive? Are the gram amounts of solute and solvent additive? You know, convert between grams and moles. So, you know. I think they're fun. These ones are fun. Navigating units and understanding the difference between solute, solvent, and solution. All right, so let's do, we're going to do another one? Oh, a different one. Okay. Vapor pressure, vapor pressure. Yeah. So all liquids exert vapor pressures. When their vapor pressure equals that of atmospheric pressure, that substance boils. Okay, so at room temperature, some liquids are smellier than others, meaning that they exert more vapor pressure. So here's an example. Water, we have pure water and pure ethanol. Okay, just from your human experience, does water smell like anything? Does ethanol smell like anything? Yes, it does. So ethanol, you see, has a higher vapor pressure at room temperature, right? Because it does smell like something, all right? So if we had pure samples of either of these, if we had pure water, it would exert a vapor pressure of 175 torr, pure ethanol, 400 torr, if it was pure. But where things change is when we start mixing them, right? So like, for example, vodka is 40% ethanol. Does vodka smell like anything? Yes, it smells like ethanol, because you're smelling or you're experiencing the vapor pressure being exerted by ethanol, right? The water contributes a little bit of vapor pressure as well, but not as much, right? So we can calculate the total vapor pressure exerted by mixtures by including the mole fraction of each of the components. So here we are mixing, what is this, 125 grams of water and 85 grams of ethanol. Okay, so just from those masses, we should be able to get mole fractions of each of those. Mole fraction of water, mole fraction of ethanol, that should add up to 1. Because how we calculate the total vapor pressure is we just take the mole fraction of each of those components, multiply it by its pure vapor pressure, all right? And then we add those two components together. So there's ethanol's contribution, this is water's contribution. It's kind of just like a weighted average. But the hard part is, can you calculate the mole fractions of each? But we can from the data that is given. So what I want to do is actually convert those gram amounts, all right, to mole amounts. And that's going to get me closer to mole fraction. So 85 grams of ethanol, I give you the molar masses. So ethanol is 46.07 grams, 1 mole of ethanol. Water is 18 grams, 1 mole of water, right? So this solution contains 1.845 moles of ethanol, and then I also have 6.937 moles of water, both of those. So for funsies, I can just go ahead and add those two numbers up because I'll need that for my denominator. So the total number of moles of just stuff I have, which is just, again, these two numbers added up, that's going to be my denominator, is 8.782 moles of solution. So when I go ahead and calculate mole fraction here, okay, when I go ahead and calculate move some stuff around, I'm just going to take the mole amount of ethanol, so 1.845 moles of ethanol over total, so 8.782 gives me some fraction, and then the rest of it is water, 6.937 over 8.782. And so we get that the mole fractions of each of those components is something like 21% ethanol, and then we have 0.7899% or fraction of water, right? So 79% of it is water, about 21% of it is ethanol in terms of moles, mole amounts, all right? So really what I did here is I converted grams to moles, calculated the mole fractions by summing up the mole amounts in the denominator, right? And so these numbers that I just got, that's what's going to go into my Raoult's law, right? Where we basically are treating this like a weighted average. So those values to calculate the total vapor pressure of this solution, I want to take the ethanol contribution. So 0.2101 of it is ethanol. Pure ethanol has a vapor pressure of 400 torr, but I only have 21% there, so that's why that contribution is slightly lower. And then I add water's contribution. So water is 0.7899 times the vapor pressure of water in its pure form, so 175. So we'll see that the vapor pressure of this mixture is somewhere between 400 and 175. That's water's contribution, and so we just add those things up, and we see that, I'll go down here, go down there. Okay, so that's water. That the total vapor pressure of this solution is 224. Right. So if I would put my nose above this solution, all right, that has both 85 grams of ethanol and 125 grams of water, I stuck my nose in that vapor that's above the solution, my nose would read 222 torr, right? That's the total vapor pressure though, right? Okay, so the follow-up question here says, what is the mole fraction of ethanol in the vapor phase? Okay, this one's a little bit harder. What a lot of students will say is 21.2101 or whatever, 21%. A lot of students will say that. But that's the mole fraction of ethanol in where? In the solution. Yes, in the solution. So we want, what is the mole fraction of ethanol in the vapor phase? It's not that bad, all right? It's not that bad. So in the vapor phase, think about what is in the vapor phase. Okay, what is going on? What the heck? No. Okay. In the vapor phase, okay. In the vapor phase, we have a total of 222 torr. Some of that pressure is coming from ethanol, some of it is coming from water. So when we did this addition, all right, ethanol was actually contributing, if we do that math there, ethanol is contributing 84 torr. Like when you do that math, I think. When you do that math for water, water with its mole fraction is actually contributing 138 torr, right? That's coming from water. Both of those added up, you get the vapor pressure. So to get the mole fraction of ethanol in the vapor phase, we just take ethanol's vapor contribution and we divide it by the total vapor pressure of that entire system. So we see here the mole fraction of ethanol in the vapor phase is 84 torr over 222 torr, and that equals something like 0.378 torr. Or not, sorry, it's a fraction. It's not torr, all right? So 38% of the particles in the vapor phase of this solution above the solution in here. If you counted all the particles, 38% of them are going to be ethanol particles. But if you counted the particles in the solution, only 21% of those particles in the liquid phase are ethanol. And so that's the difference. How would we calculate the mole fraction of water particles in the vapor phase? There's a couple ways you can do it. You could subtract this from 1. Yeah, and so if you subtract that from 1, so 1 minus 378, you get that the mole fraction of water in the vapor phase is equal to 0.622. All right, so 62% of the particles in the vapor phase are water. Another way you can do it is the same way we did ethanol in the vapor phase. We just take, okay, what's water's contribution? So 138 torr over 222, and you will get the same number. You'll get the same exact number, I think. 138 divided by 222. Yes, you get the same number. All right, so that's the big difference. So a little bit of reading comprehension. Are they asking you mole fraction in what? Is it in the solution or is it in the vapor phase? A little bit different, all right? So there's that. Okay, all right, let's keep going. Okay. Okay, all right, so let's do some freezing point depression. Yes. Okay, so freezing points, if you think about the freezing point of water, the more junk you add to water, the more stuff you dissolve in water, the freezing point changes how? It goes down. Yes, it goes down. So we did some examples in class where we calculated the boiling point elevation of maple syrup, right? The boiling point elevation of maple syrup is like something like 3 degrees Celsius or something. So that means, does maple syrup boil, or does it freeze above 0 degrees Celsius or below 0 degrees Celsius? If I tell you that maple syrup has an elevated boiling point temperature, maple syrup will freeze below, yes. So if a solution has a freezing point depression, it also has a boiling point elevation. Actually, so there was a really good exam question. This was an exam question. I tricked a lot of you guys, where I said something like, okay, I give you the KF and the KB of water. I don't remember what these numbers are. I think it's like, okay, I'll just look it up. I just looked it up. Okay, here's the scratch paper that you're gonna get. There you go. Okay, so the KF of water is 1.86 and the other one's 0.51. I think I knew that. 0.51 degrees Celsius per molal. And then freezing point depression is, what was it, 1.86 degrees per molal. Okay, so I told you, you have some unknown solution. Okay, you have some unknown solution and it has a freezing point of negative 0. Let's say 93 degrees Celsius. You have some unknown solution. That's the temperature it freezes. Okay, it's a water solution, it's aqueous solution. And I asked you, what is the boiling point temperature? So this is the freezing point. I asked you what the boiling point temperature was. And one of the options was, I didn't give you enough information. And a lot of people said that. Yeah, so let's think about the equations for both of these. So the equation for freezing point depression is, right, the delta T equals I M Kf, right? And then the equation for boiling point elevation is I M Kb. So based upon this freezing point data, I have the freezing point depression. It got depressed 0.93 degrees. Kf is a constant. So doesn't that allow me to calculate what Im is? And if I know Im, can't I just shove that in there? Yep. With the new freezing point, with the new boiling point constant. So putting all of this together, this was like an exam question that a lot of people got wrong. Putting it all together, so I think there's a negative sign there to make it all good. 0.93 equals negative Im. So I'm basically calculating that together. I don't really need to know whether it's an electrolyte or a non-electrolyte. I'm just calculating how many particles are in solution. Times Kf, so 1.86 degrees Celsius per mole Wow. So that means Im, whatever that is equal to 0.93 divided by 1.86, 0.5 mole Wow. All right, and so that's what I'm going to plug into my boiling point elevation equation. So I know what Im is. So boiling point, oh, what is this? That's a pen. Boiling point is equal to the 0.5 mole Wow, but now we multiply by the boiling point elevation constant. So 0.51 degrees Celsius per mole Wow. So we see the boiling point elevation is something like 0.255 degrees Celsius. So that means the boiling point of this solution is what? 100, yeah, 100.255, whatever, degrees Celsius, right? So that's how we were able to do it. All right, we did have enough information. It was just with the information given, we were able to figure out how many solute particles were present, the total number, to yield that freezing point depression. Right? Okay, so we actually never answered the question. But this triggered me, and I remembered that I was sad that that question did poorly. Okay, using ion pairing, rank the following aqueous solutions in increasing freezing point. So remember, more stuff dissolved, more solute particles in solution, lower the freezing point. So we want increasing freezing point, so pure water should have the highest freezing point, okay? Because anything else that has stuff dissolved in it is going to have a lower freezing point, right? So for all of these, you know, think about freezing point depression as I, M, Kf. All of them have the same Kf, so I want to figure out what is Im for all of them, because that's going to allow me to figure out how many total solute particles there are. So the first one is glycerin. Glycerin's a non-electrolyte, so its I times M is 0.2 molality. Right? That for every 1 mole of glycerin, you just get 1 mole of glycerin dissolved. But that's different for something like KCl. It's ionic, so you put one thing in, you get 2 things out. You get a K plus and a chloride. So its I times M isn't 0.1, it's actually 0.2. I hope you see where this is going. Yeah. So calcium sulfate has an I times M of 0.2. Oh no. So at first glance, those first 3, it looks like they all have the same number of solute particles present. Okay. But then the last one, calcium chloride. This one is different. This one has an I times M because we have 1 calcium and we actually get 2 chlorides. This actually has an I times M of 0.3. So we can clearly see that this one has the most solute particles dissolved. So this one's going to have the lowest freezing point. It's these 3 that look the same. They all look the same. So we know the highest freezing point is pure water, and we know that the lowest freezing point is that 0.1 molality calcium chloride. Okay, it's just all the middle ones we don't know. And it's a little bit confusing because we see that they all have the same I times M, but the tip is here that the question says use ion pairing. So ion pairing explains deviations from the Van 't Hoff factor I. When things ion pair, I changes how? Typically goes down. Yeah, when things ion pair, your Van 't Hoff factor decreases away from what it should be, okay? Because ion pairing, it's like, okay, yes, we make free sodium plus, all right, or I guess calcium or potassium plus. All right, we do make potassium plus and chloride minus in solution, but if at a certain moment a potassium ion is attracted to a chloride anion, all right, those two particles become one for like a moment in time. And so it lowers the total amount of dissolved solute particles in that solution. So I think the trends for the Van 't Hoff factor and deviations with ion pairing increases more. So you get more ion pairing, meaning that you see a decrease in your like perfect I value, the predicted one, the ideal one. Ion pairing increases if concentration is high. What is the other ones? When charge is high, yep, when charge is high because your ions are more attracted to one another, more likely to ion pair. And then the last one is if size is small, right? Okay. Also, there are things that cannot ion pair. What are things that cannot ion pair? Non-electrolytes. So what in these three examples that look like they have all the same I times M? Glycerin. Glycerin is the only one that does not ion pair. So that means its I times M is exactly 0.2. Exactly. It's the other ones that actually contain ions that have their I times M deviate a little bit. So let's look at these two examples. Calcium chloride or potassium chloride and calcium sulfate. Both of them have an I of 2, but one of them deviates more. Which one? And for what reason? It's the charge, it's calcium sulfate. Yeah, so this one deviates the most. It deviates how? Is calcium sulfate's I times M 0.2? No. Is it higher than 0.2? No, it is lower, and it's much lower. It's much lower than 0.2, while KCl is just a little bit lower than 0.2, while glycerin is exactly 0.2. So putting this all together then, of these three, which one has the next lowest freezing point? Glycerin, yes, because it has the most particles present, because it's the most concentrated. So it's the glycerin one, all right, and then next it's going to be KCl, all right, and then the last one is going to be the calcium sulfate, right? So we looked at charge being the deciding factor. Calcium sulfate has a higher charge, more likely to ion pair. What we didn't look at was concentration, because both of them actually have the same concentration, so that's not going to make a big difference, right? All right, so there's that one. That's a conceptual question, very conceptual. Okay. All right. All right, so that's chapter 13. So let's keep going. Chapter 14. Given this rate constant, what is the initial reaction rate when the initial concentration of A is this concentration? Like, do you remember how to do this? Yeah, okay. Rate laws. So rate for a reaction is equal to K times concentrations of stuff to some order. So it looks like I give you K, I give you concentration. I don't know the order of this reaction, or do I? You do, right. What is the order? It is first order, yes. There's a couple ways you can get this. Okay, recognize that rate of a reaction is in molarity per second. So if rate constant is 1 over seconds, I just need to multiply one molarity concentration to get that unit, so it's first order. So actually putting all of this together, rate equals 6.2 times 10 to the negative 3, and we're just going to multiply by that concentration, 0.01 molarity, and then that's it. So I guess the rate, initial rate is something like 6.2 times 10 to the negative 5 molarity per second. That's what it is. Yeah, so great. Yeah, and so that's the tricky thing here, is recognizing what is the order from the rate constant unit. I could have made it a much easier question if I would have told you what the order was. Like, oh, for this first order reaction, this is the rate constant, and then it's just plug and chug. So this is what elevates the question a little bit more. Recognize what's the unit for different orders. I told you you never have to memorize it. You can always like figure it out on your own, what the unit of all of the rate constants are. But at this point, have you just kind of memorized them anyway? Yeah, so for a 0th order reaction, if n is 0, the only way to make this side of the reaction equal molarity per second is if K was equal to molarity per second. That's the only way, okay? If it was first order, all right, that means we have one molarity we have to deal with. K is equal to second to the negative 1, or 1 over second. If it's second order, we have two molarities here we have to deal with, and I think K is equal to molarity to the negative 1, second to the negative 1. Right? The time unit can be anything. It could be minutes. It could be years. Right? It can be anything. Right? If you remember, we were doing nuclear chem, right? Our rate constants, they were always some time to the negative 1 power because radioactivity is always first order kinetics. Okay. All right. Let's keep going. Okay, mechanism. The reaction between NO and O2 is believed to occur with this mechanism. So it looks like it's a two-step mechanism. What is the rate expression if this mechanism is correct? So what's the trick with mechanisms? The slow step determines the overall rate. So in mechanisms, that is the only time you're allowed to just take the reactants and that becomes the rate law. That's the only time you're allowed to do that in mechanisms with elementary steps. So this to me indicates that, oh, there's my slow step. So the rate of this slow step is equal to K, I'll just say K2, times NO3 times NO. So am I done? Is that my rate law? No. What's wrong? Yeah, there's an intermediate. We're not allowed to have NO3 in there. So should I just take it out? No, we got to do a little bit of finagling to get rid of that. So I need to get rid of that intermediate. So this is where I use the fast step. The fast step says that the forward reaction rate is equal to the reverse reaction rate. So I can say K1 times NO times O2 equals K negative 1 times NO3. And so I just move the K's around. And so we see that the concentration of NO3, the intermediate, is actually dependent on the concentrations of NO and O2. So I'm going to use this fast step, the forward equals reverse step. I have it rearranged, and I'm going to substitute this in for that intermediate that I'm not allowed to have. So we see that the rate is equal to, I'm just going to call it an overall K. There's a bunch of K's in there, but we'll just see it, K overall. It's going to be NO squared, and then an O2. I didn't give myself an O2. And then an O2. O2. There we go. Once I substituted those concentrations in for that intermediate. All right. I think the exam, The midterm one, I put a question on there. You know, there was basically two rate laws or mechanisms I showed you. Slow first step, that one's easy. It's just like that's the the reactants are your rate law, right? And then the harder one is like this one where it was a slow second step, right? But on the exam, do you remember what I gave you? It was a slow third step. But the most of you got it because the rules still apply. When the third step was slow, it was still, the slow step determines the overall reaction rate, but the difference there was that there were just two intermediates you had to get rid of. That was the only difference. The majority of you got it. Okay. Very good. All right, so let's look at another way we determined rate laws, and this is the method of initial rates. Where I change the concentrations of my reactants and inspect, okay, how fast does my reaction go? And so depending on how I make those changes and how the rate reacts to that or changes to reflect that can tell us about the overall order. So we actually see it's the same reaction as the one up here, but it's just a different method we use to inspect the rate law. So here in the previous one, we see, this reaction second order with respect to NO and first order with respect to O2. So let's see if this data agrees with that. So in these experiments, the idea is you want to look for experiments where one of your reactants is staying constant. So in this example, O2 is staying constant between reactions 1 and 2, or experiments 1 and 2. And then I think to myself, okay, how is concentration of NO changing? It looks like it's doubling. So NO concentration is doubling, O2 concentration remains the same. So I know that O2 is not affecting any changes in rate, but then how is the initial rate changing? It is times, is it 4? Yes, times 4, yes. So if I double NO concentration, but I see a 4-fold increase in my stuff, what does that imply about the order of NO? It is second order, yep. If let's say I saw a 3-fold increase in NO and I saw a 9-fold increase in rate, initial rate, what would the order of NO be? It would still be 2, yes. What if I did a 3-fold increase of NO, but I saw a no increase in initial rate? What would that imply? 0th order, yep. Okay, good. What would a first order look like? If why am I stupid? Why is this? I don't know what. All the buttons look the same now. What would this look like if this was a first order reaction with respect to NO? It'd be times 3. Yeah. Okay. Good. All right. Good. So let me put the right answers back. So 2, 4. All right. So now we have the order of NO. We're gonna now use reactions 2 and 3 to figure out the order of O2. So we're only halfway done. So recognize that NO is not changing, so we don't need to think about how that's affecting our rate. But O2, it looks like it's doubling, and then how is the initial rate changing? I think it's also, yeah, it's also doubling. So that implies that O2 is first order. All right. Is that it? Oh, I didn't even ask a question. Yeah. But for funsies, let's do the whole rate law. Is this the whole rate law? No, it's not actually. What am I missing? K, the rate constant. So we can actually calculate the rate constant. How do we do that? Yeah, just plug in any numbers. So from one reaction. So let's just use number 3. All right. So this is saying, the initial rate, 1.13 times 10 to the negative 1 molarity per second equals K, the rate constant, that's what we're solving for, times NO concentration, 0.0252 molarity, squared, because NO concentration is, second order, times concentration of O2, so 0.2025 molarity O2. And then we get something like, oh, I did calculate K in the key. So K equals 7.1 times 10 to the 3 molarity to the -2 second to the -1, all right? And so then combine that with my orders, that is my total rate law, right? And so you should calculate the same K for using any of these experiments in theory. So I in the key used experiment 1, but here I had the values for experiment 3. So let's see if we get the same number. We should, or if we don't work, 0.0252 squared divided by 0.025. Yes, like 7,100. Yep, good. All right. So these two were the two ways to get a rate law. So method of initial rates, we just did that. Then we did mechanisms. And then the third way to get a rate law was how? Graphing. By graphing, yeah. Which I don't have you do. But when we graph, remember this is like your bar lab. What are you looking for when we're graphing? Straight lines. Because when you have a straight line, it implies that your rate, that's your rate constant. You have a constant rate constant. And wherever your graphs are linear, most straight, implies that that is the correct order of your graph, because it's fitting the integrated rate law, where either your concentration units are as is, that's 0th order, first order is what? Natural logs, and then your second order is 1 over, right? Where your slope of those straight lines is related to your rate constant, if you have 0th, first, or second order. So first you need to figure out which order it is, and then you get your rate constant from the appropriate graph. All right, so that's kinetics. So let's keep going. K stuff. Big K. So rate constant was small k, baby K. So now we're talking about equilibrium constant, big K. So here the equilibrium constant for this reaction is that. We have a system at equilibrium. Here are the concentrations. What is the concentration of methane? So in this question, I tell you everything is at equilibrium. So we just plug everything into the K expression, right? And we just solve for the missing piece. So 3.93 equals products over reactants. Since this is Kc, everything can be in concentration. So CH4, H2O, H2, but it needs to be cubed, and then CO gas. And so I think we're just solving for CH3 and that missing piece. So CH4, sorry, water concentration is 0.0478. Molarity, H2 is 0.1566 molarity, but that is cubed, and then CO is 0.1522. And so we're just solving for CH4. And again, I said it's at equilibrium, so we can just plug everything. No ice table needed, because we are already at equilibrium. So CH4 concentration is 0.0481 molarity. That's the missing piece. You can check yourself by putting all of the numbers into the K expression and seeing if you get that correct Kc out. Right. Okay, so this next one, what is the value of Kp at this temperature? So the equation we want to use that relate Kc and Kp, let's just quick look at the scratch paper. Which equation do we want to use? Kp equals Kc times RT delta N. That's the equation we want to use. So we are solving for Kp equals Kc. So that means we're using that 3.93 number, okay? Times R, what R do we want to use? 0.08206 liter ATM mole Kelvin. Then I use temperature. What's my temperature? Is it 298? I know we use a lot of 298, but is it 298 here? It's 1200. Yes, it's 1200 Kelvin. Okay. Times delta N. What is delta N here? Change in moles of gas. So we look at total moles of gas on the products and the reactants. So I have 2 moles products, 4 moles on the reactants. So do look at the coefficients. So what is delta N? 2, -2. It's always products minus reactants. So it's 2 minus 4, so to the -2. All right, that's it. Okay. If it was the other way, if I gave you Kp and I wanted you to calculate case, no tail. If I gave you case P and I wanted you to calculate case C, you use the same equation, you just swap in, right? Okay. The hardest part is that delta N thing. All right. All right, and then you get your answer. Okay. Let's keep going. Okay, 1 mole of A is placed into a 1 liter container and we heat it up. Substance A decomposes according to this reaction. At equilibrium, the concentration of B is blah. Calculate Kc at this temperature. Yes. Ice tables. It's ice table time. But let's set it up, okay? Don't get scared until you set it up. It might be easier than it looks. So with ice tables, okay, so remember we did like molar or BCA tables, and so with BCA tables, you needed to be in the unit of moles. But what is the unit you want to be in for ice tables? Molarity if it's Kc, pressure if it's Kp, okay? So I give you Kc, so we want to be in molarity. So do keep that in mind. All right, so what is the initial molarity of A? 1, yes, 1 mole in 1 liter. I tried to make it easy. Right? So that's the only thing in the container initially, so I have 0 of everything else. So which way does this reaction have to go? Forward. Okay, so now I know which way my change line is going. It's going forward, but we need to make sure our change line reflects the stoichiometry. So I'm going to have minus 2x, yes, minus 2x. I know we've done a lot of acid-base chemistry, and it was always 1 to 1 to 1 to 1. We always have to follow stoichiometry. Plus x, because the other two are just 1 stoichiometry. And then we add up our columns. So at equilibrium, we have 1 minus 2x of A, x of B, x of C. Right? Then we can go ahead and plug those into our Kc expression. Right? Kc is B concentration, C concentration, A concentration, but it's squared. Right? At equilibrium, it's squared. Yeah. And so this is where a lot of students will go, oh, it's x squared over 1 minus 2x. I'll just make a approximation and just do this. Nope, you don't want to do that. Because this is what kind of ice table? It's a type 1 ice table, where I actually give you a hint. What's the piece of information we did not use yet? Yeah, concentration of B. And what is concentration of B? X, yes. So if I give you concentration of B, which is 0.025, I actually told you what X is, all right? And so, yeah, if we put in that equilibrium line into our K expression, it becomes x squared over 1 minus 2x squared. You know what X is. Just plug it in. Okay, if you make an approximation down here, what do I say if you read it in my key? You're being lazy, right? Because what's the point of the approximation? It's to avoid the quadratic. Yeah, so we know what X is. Just plug it in. Plug it in because you know what it is. And so this would then reduce to 0.025 squared minus 1 minus What's 2.5? So 0.05 squared. That is not a quadratic. That's just like a tiny bit of math, right? So I think you get 0.025 squared divided by 1.05, wait, 1 minus 0.05 squared. Okay, so I get 6.93 times 10 to the negative 4. Yeah, so don't be lazy. But for funsies, let's see if what you would get if you were lazy. If you were lazy and did make an approximation and just go like that, let's see what number you would get. It's still going to be close. Okay, so if you were lazy and you made the approximation and you plugged in x, you would actually get 6.3 times 10 to the negative 4. So it's a this is with the or like, you know, this is actually wrong. So I should write that. This is wrong. This one is right. Right? So if you, I think I had a question like this on midterm 2. It was like, here's a weak acid with this concentration. Here's its pH. Tell me Ka. And I had both options. I had this one. This is 1 Ka. This is the correct one where you don't make the approximation. And then I had, if you did make the approximation and you got rid of that minus x at the bottom. And I had both there, but only one of them was correct. So this one is wrong. Look, the K is actually quite different, right? So it is quite different. Don't be lazy. The quadratic is, or the approximation is just supposed to avoid doing the quadratic formula, right? You know what x is. You don't always have to make an approximation. All right, so this one's a type 1 ice table where you're given essentially all the information you need to fill out the ice table so you can calculate K, while this one, 25, that we did in class today, you fill out your ice table, but I give you K, so you have to figure out what X is. That is what may require the quadratic. All right, so that's a little bit different, where we are trying to figure out the equilibrium line in 25, but in 24, I actually gave you a hint to filling in the equilibrium line. All right, because we know what X is, we could actually calculate the concentrations of everything at equilibrium if we wanted to, because it follows stoichiometry. All right, so that's 25. All right, so that's midterm 1, done. 45 minutes. Can we get through midterm 2? How many more pages are there? A lot. What was harder, midterm 1 or 2? 2. But it was, midterm 2 was just about K. Yeah, we don't like K. Just remember, K, it's products over reactants. Get you out of a lot of jams. All right, so let's calculate the pH of these things, all at 25 degrees. So you need to ask yourself, okay, pH means negative log of H plus concentration, right? I read on Reddit, like just yesterday, like some article, the person who invented the pH scale, they don't even know what P stands for. I don't know how true that is. I don't know what P stands for. I assumed it stood for power, like hydrogen power. I don't know. But like P doesn't stand for anything. I don't know. I just know P means negative log of, but that's like not what it means. I don't know. I read it on Reddit like yesterday, I think. Okay, so with all of these pHs, I know I have to negative log it to get a pH, but you need to ask yourself, what is HCl, and how will I go about calculating how much H plus there is? HCl is a strong acid. So how do I calculate the pH? You just negative log it, yeah. For funsies, let's remind ourselves, what are the 7 strong acids? Don't go in order. Go in order. HCl, HBr, HI. I know you all jump in the gun. Okay, so those are like the easy ones. Those are the binary acids, HCl, BRI. HF doesn't count. That's like the most common weak acid we talk about. Yes, HNO3 is one, yep. So now the poly, or the oxy acids, they're a little harder to memorize. H2, or yeah, H2SO4, H2ClO, which, 3? It's 3 and 4. So yes, H2, or no, sorry, it's not H2, it's HH1, yeah. HClO3 and HClO4. Yeah, both of them. So those are the 7 strong acids. So if you have any of those, you just negative log it, okay? All right, so this one, strong acids, so pH is negative log 0.049, and so you get something, you get a pH of 1.31. Is that acidic? Yes, we put acid in, so it's acidic. Very good. All right, this one, sodium hydroxide. It's a strong base, so I negative log it, but that gives me POH. So the POH is 2.82, so that would make the pH, and since this is at 25 degrees, we can just do the 14 minus POH equals pH equals 11.18. Is that a basic pH? Yes, it is. Good. All right, calcium hydroxide. This is the one I was so disappointed. Did so poorly on midterm 2. Supposed to be easy one. I think I even had a Kahoot that was like this, because I did sodium hydroxide right next to calcium hydroxide. So what a lot of students will want to do is just do negative log 0.0015 again, but is the concentration of hydroxide 0.0015? No. Hydroxide concentration in this substance is actually 0.003. Yes. So we want to actually negative log this to get POH. So POH is a little bit, actually more basic. There's 2 hydroxides for every 1 calcium hydroxide. So POH is 2.52. That would make pH 11.48. So we see that the calcium hydroxide solution is actually more basic than the sodium hydroxide. And that makes sense because there's twice as many hydroxides there. Right? So, since I'm going on vacation, I asked my neighbor kid to watch my farm animals, and like he came over and he had these big bandages on his knees. And I'm like, oh, what happened? Like, and he's like, oh, you saw us pouring. Their family just built a garage, and they were pouring cement the other day. Yeah, he was pouring cement, and I'm like, oh, you must have gotten a chemical burn off of kneeling in the cement, in the wet cement. And he's like, I don't remember if it was like acidic or basic or something. And I'm like, oh, it's probably basic from like the calcium hydroxide that was in the materials. Cement is full of like calcium carbonates and stuff and like inorganic things. And yeah, just having that in contact with his knees, he must not have like cleaned it off fast enough. And yeah, he got chemical burns on his knees from the calcium hydroxide. He said something like, it must be like acidic or basic or something. I'm like, oh yeah, it's super basic. Yeah. So. Are in what? Yeah, we talked about airbags. Sodium azide. It burned you? Uh-huh. So the thing is, sodium azide's a solid. I don't know what else is in there. I don't know. I've never experienced sodium azide, but no, I believe it. I believe it. Working with azides are really dangerous because in like labs sometimes. Actually, okay, so like chemical hygiene and safety is super important. I was actually vice president of the joint safety team here at OSU for many years because chemical safety is very important to me. I think it was in Texas. There was a research group working on azide chemistry. So sodium azide is NaN3, so like 3 nitrogens bonded to one another. And oftentimes in organic chemistry, before you do a reaction, you grind your materials together if they're solids. Because if things are finely ground, then there's a lot of surface area. Or if you finely grind it, then your stuff dissolves faster, right? And so, but azides are explosive. That's how it works as an airbag. And this, I think one grad student was grinding some azide and it blew his hands off. He lost his hands. Yeah. Yeah, it is horrible. It is horrible, yeah. Yeah. Yeah, creosote, yep. Mm-hmm. Well, yeah, so creosote, even just wood ash is very basic, right? So is anyone a crunchy mom and make their own soap? No? No, okay. So making your own soap, like lye-based soaps, well, actually, where the word soap comes from, and you'll learn this in organic chemistry about saponification, the process of saponification, where you take animal fats, you saponify them, so you put them in contact with really basic environments to turn the fatty acid into a acid salt, right? And so you need really basic environments to do that, and wood ash does that. So they oftentimes say, like, wood ash, if you make fires, like, don't try to fertilize your blueberries with wood ash because it's really basic, and blueberries require really acidic environments, okay? So wood ash and creosote both are very basic. So your dad, if he has chemical burn scars, is just like what my neighbor kid has with calcium hydroxide, burns on his knees. Yeah. Oh, really? Interesting. Well, that is kind of an embarrassing thing because people, value their hair. But the thing is, with bases and acids and stuff, like, it's not dangerous as long as you wash your hands very soon after. So if your dad was working and like constantly rubbing wood ash all over his skin and not washing it off, then that's bad. If you ever, like, in lab, do you ever touch sodium hydroxide? Like when you're doing titrations, do you ever accidentally touch it with like your bare skin? It feels soapy. Yeah, your hands get slippery. You know why it gets slippery? It is. Well, it's actually saponifying your skin, all right, slowly. But the thing is like that's how soap works. Anyway, if you've ever used real soap, it feels slippery because literally it's the hydroxide is like eating away at your skin just a little bit. But again, washing it off there's no big deal. If you get a tiny bit on you, you wash it off right away, you're fine. But it's if you leave it there, it's really bad. Because I remember once I used to, back in my day, like I wear short boots. I used to wear long boots, like long, I don't know, not cowboy boots, but like long boots. And sodium hydroxide pellets, there were little pellets, and I was in lab, and I let one fall into my boot. And I didn't know, and so it was sitting next to my sock all day until like I went home and it was like partially melted like into my sock. It was just one tiny bead of it. And I had a little tiny circular scar like on my foot for a long time because it just fell into my shoe and just like stayed there all day. Because I didn't wash it off. So there are your side stories. Basic. All right. I was in a chemical accident, but it was with an acid. I already told you about it, right? No? No? No, yeah, I was in a chemical accident where nitric acid exploded in my face. Yeah. It was a waste container, so it was like concentrated nitric acid exploded in my face. I had to go under the safety shower. It sucked. Yeah. And then I had to go to the ER and stuff, and I didn't tell you guys this? Okay, all right. And then I was fine. Don't worry about it. I was only disfigured for like a week. But here's the thing. Nitric acid is it's an acid, right? It's a strong acid. But it was only in contact with my skin for maybe 30 seconds before I washed it off and I went under. Well, at first I went to the sink and like was just copiously washing everything off my body. And then they made me get under the safety shower. Yeah, and then we went to the hospital, all that thing, it was fine. So what happened is it just it was just a very superficial, like, chemical burn on my face because it, again, was only on my skin for just a couple seconds. And so my face turned red, it then scabbed, and it peeled off in like a week. It was great. Because the thing is, some people deliberately put acids on their face. Have you ever heard of an acid peel? I get that all the time. With glycolic acid or salicylic acid, acid peels, like people do it deliberately. So after it scabbed and I peeled it all off, it was just like baby smooth skin afterwards. But the thing I say, about this is they asked me to go to my general practitioner after I had the accident. And so, like, I was telling her what happened. I was like, oh, yeah, nitric acid exploded in my face. And so this is my doctor, right? And she's like, nitric acid. Is that like an acid? I was like, yeah. Yes, it is an acid. Yeah. And so unfortunately, so she saw me, it was all fine, but she's like, here, I'll prescribe you some silver sulfadiazine. It's a burn cream, silver sulfadiazine, right? For your face. But I don't know if you guys remember, I told you that I'm actually allergic to silver. And so when I put the burn cream on, I had a really bad allergic reaction, and then I had to go on steroids to fix that. So, like, the burn was fine. It was all the other things that were bad, right? And so that happened in my undergrad, and I'm still a chemist. I value chemical safety, and so, yeah, don't let that stop you. Achieve your dreams. Like a real long time. Like a real long time. Because they didn't know what to do with me. Because it was, my undergrad, it was like the first accident that's ever happened. So everyone was pretty scared, yeah. They actually kept my clothes. So I think back in undergrad, I wore the same thing I wear now, like librarian clothes. So the acid actually ate away at my clothes. So when I was in the hospital, I like changed in pajamas and stuff, but the department asked if they could keep my clothes. And they show it every year because they show it every year. Like my sweater has like all these like massive holes in them because the acid just ate away at the stuff. Yeah, I was wearing, so jeans are actually the most protective thing you can wear in lab because they're very absorbent. It's very like densely knit. Yoga pants are the worst thing to wear because if you got a little bit of acid in like on them, it would just soak right through. But with denim, it's a lot more safe. Yeah, so they keep my clothes and they show it every year. But now they value chemical safety a lot more there. And since at OSU we take pride in the safety culture we have here, that was a really nice transition. And I know talking to my undergrad people, they've taken more initiative in how they teach students chemical safety. Yeah, because like here, even in the Gen Chem labs, I feel like they do a good job. They tell you like, put your stuff in this one, not this one. Tell us when it gets to a certain height so your TA can neutralize it. Like, it's not like some secretive thing, how we dispose of waste. I hope so. But, we do make an effort for it, so. I told you that. I told you that. I said, if you have any skin below the belt showing, you're not getting in the lab. Yeah. Yeah, no, yeah, no, that, like, look at me. Everything I wear every day, I'm lab ready, right? See, my husband calls these my high water pants. But look, I have the fun socks on, so it does cover it. I just have to hike them up a little bit, all right? Yes. I know, actually, one of my TAs, because at least you have lab coats now, one of my TAs who I used to teach, she said she used to, under her lab coat, just pull her pants down low enough to cover her ankles. But because she would like, I think she would sit the whole time anyway, so like it didn't matter. So like, and it was, her lab coat was covering it, so she had probably like her pants were down like this. But I don't know. I told you guys. I told you. I know. You don't believe me? And capris are coming back, so I think, yeah. So, what? Yeah. Oh, they aren't? Okay. Well, I'm just saying, I see a lot of ankles now than before. All right, sorry, we're 30 minutes. Okay, let's keep going. All right, pH. What is this? It's a weak acid, so can we just negative log this? No. We can do an ice table, yeah, but do you want to do the lazy ice table? Yeah, so it ends up just being x squared over 0.02 molarity equals what? The Ka, yeah, because this is an acid, we are fine to just use the Ka there. And so when we solve for x, what is x? The concentration of H plus because we used Ka. And so this is 4.47 times 10 to the negative 3 molarity. And so the pH is 2.35, right? So this is I basically did the approximation here. So this is your Ka ice table. There would have been a minus x on the bottom here, but I just got rid of it because Ka is really small. Right. Okay, next one. NaA, what is that? That's a base, yes. So can we use Ka? No, we use Kb. How do we get Kb? Kw over Ka, which is equal to, can you just calculate it in your head? What is Kb? 10 to the negative 10, yes. Equals x squared over 0.02. All right, when you solve for this, what is x? Concentration of what? Hydroxide this time because we used Kb. And so this is equal to 1.4 times 10 to the negative 6 molarity. So we get POH equals 5.85. We get a pH is 8.15. Does that pH make sense? You put a base in water, your pH is basic. Okay, 0.02 molarity of B, a weak base. How am I setting this up? X squared over 0.02 is equal to what? Kb, yep, because it is a base. Or B is a base, it's Kb. So equals 1 times 10 to the negative 5. We get X is equal to hydroxide concentration because we're using Kb. This is 4.47 times 10 to the negative 4. POH is equal to 3.35, so therefore pH is 10 something, 10.65. And again, basic pH, we put a base in water. Is the next one a base? I know there's a lot of crap there, but just break it up. What is that? Nitrate. Do we usually care about that? No. We care about the other thing, HB plus. What is that? That's an acid. That's the conjugate acid of B, base. So this is equivalent to NH3 ammonia and NH4 plus ammonium. This is the equivalent thing, right? So we're still going to do x squared over 0.02 molarity, but we don't want it equal to Kb. We want it equal to Ka this time because Hb plus is an acid. So we're going to use the Kb that's given. That is 10 to the negative 9, I think. Yeah, right. And so then we solve for x, and it is equal to H plus concentration. We get that that's equal to 3.16 times 10 to the negative 6. So pH equals 5.50, right? We put an acid in solution, it became acidic. The hard part here is just recognizing, okay, what substance am I actually looking at? What K am I given? Am I given B, HB plus? Am I given HA, or am I given A minus? Those are the combinations. Okay, HA and A minus have a Ka associated with them. B and HB plus have KBs associated with them, but you need to make sure you're using the appropriate one, right? And so for all of these, D through G, we are using the approximation, all right, approximation. So in all of them, I skipped the step of this minus X on the bottom. That's what the ICE table would tell you. I just went ahead and got rid of them. All right. Okay, so let's keep going. Tell me, is this acidic, basic, or neutral when dissolved in water? This thing. Yikes. Are you just guessing? So let's break this apart. So I give you a Ka and a Kb. I give you a Ka for HF, but is this HF? No. But is there something kind of present that sort of looks like HF? F minus, this garbage is like ammonium. So this is H2NNH3+. So these are the two things that are in solution. F minus is the conjugate base of HF. So F minus is a base. Hydrazinium is the conjugate acid of hydrazine. So hydrazinium is a acid. So we need to ask ourselves which one's more acidic or which one's more basic. Okay? So, but here's the thing. You told me F minus acts like a what? Base. So what kind of K do I need to describe a base? KB, but did I give you KB? No. I gave you, no, of course not. I gave you Ka. So in order to make the appropriate comparison, I need the Kb of F minus. What is that going to be? It's related to the Ka. So I'm just going to make the numbers really easy, and I'm just going to use the magnitudes. So Kb for F minus is 10 to the negative 10. That's how basic F minus is. But it doesn't automatically make it a base. If this was NaF, it would be basic, right? Because F minus is a base and sodium plus is a neutral. So like the base wins. But in this case, the counter cation is an acid. So we need to see which one's stronger. So, okay, this one. Hydrazinium is an acid, but did I give you the Ka for hydrazinium? Of course not. So what kind of K do I need? Ka. So what's the magnitude of Ka for hydrazinium? 10 to the negative 8. Okay, so now tell me, which one's stronger, the acid thing or the base thing? Acid thing. So you were right. You were right. Yeah, but see, there's a strategy into it. Yeah, there's a strategy. So you could learn the strategy if you want, okay? Because I think on the exam, did I have a similar one? I had a similar one where it was like, oh, you have H2A, so this is a diprotic acid, so this is similar. Where I said like Ka1 is 10 to the negative 4, and then Ka2 is like 10 to the negative, I'm gonna make something 8, make something up, okay? So, but then I asked you, is Ha minus acidic, basic, or neutral? Or do you not know? Okay, so let's do this. H2A is a what? Acid, it has to be an acid, yes. If I just had like Na2A, so like A2 minus, what is this? A base, but then what is this? It's a conjugate base of this, but isn't it also a conjugate acid of that? Yeah, so is it an acid or a base? It depends, yeah, we gotta look at the Kas. So Ha minus acting as a base, as an acid, is actually described by Ka1. Or sorry, Ka2, where is that, negative 8? Right? So Ka2 describes Ha minus acting as an acid. right? But we need to figure out, okay, what is the Kb for HA minus? And that actually comes from Ka1. So Kb, I think it was Kb2 is equal to Kw over Ka1 or something like that. And so we see that Kb2, so this substance acting like a base, is 10 to the negative 10. And so based upon these numbers, we see that the acid portion is bigger. So that means HA minus is an acid, right? For the same reason this one was an acid, that when we compare a Ka and a Kb, Ka is bigger. Okay? The only difference in this one is it's a little harder to figure out where do you get your Kb, right, than this one, because your cation and your anion are different conjugate systems. Okay, so there we go. Do we have any, is it an acid or base? No, we don't. Okay, so let's just keep going here. Okay, calculate the pH when we mix these things. So the strategy for all of these things when you mix them is, recognize, is it a titration, right? Am I titrating something? Am I adding a strong acid or strong base to something? Or am I mixing a acid and its conjugate already, right? So if I'm mixing, so here, acetic acid, so this is essentially HA. If I add sodium acetate to this, then that's already a buffer. I can go ahead and use the Henderson-Hasselbalch equation. But I'm instead adding sodium hydroxide, and that's how I make sodium acetate in situ. So the best thing here is just calculate millimole amounts of stuff to see where on the neutralization curve are you, all right? So I think this is equal to 10 millimoles of acid. And then how much base, strong base, do I add? This is 8, I think. 8 millimoles of sodium hydroxide. So did I fully neutralize my acid? No, I didn't. So I can do a BCA table to figure out how much stuff I have left over. So HA plus hydroxide gives me A minus plus, what is it? Oh, H2O, yeah. So my BCA table is going to use those millimole amounts. I start with 10 HA, 8 sodium hydroxide, so I'm limited by the 8. So I have 2 millimoles of HA, 0 hydroxide, and I have, 8 millimoles of A minus. And then I have some water, but who cares, right? So I have HA and A minus present in large quantities. What is that called? That's a buffer, yeah. And so these are the numbers that go into your Henderson-Hasselbalch. So we're going to do pH equals pKa. So I think the pKa of acetic acid is 4.74. Did you memorize that already? Yeah? Do you know the pKa of HF? 3.18. Plus log base over acid. So our base to acid ratio is going to be 8 over 2. If you were going to be wrong, here. You would mess up at the base to acid ratio. If a student was wrong, what's the most common mistake students put in for the base to acid ratio? 8 over 10 or something. They put, oh yeah, there's my base, there's my acid, 8 over 10. But remember, a neutralization is happening. So we want to put how much conjugate base and acid we have present. So 8 comes from sodium hydroxide. We're only left with 2 millimoles left after the neutralization reaction. All right, and so there you go. There's your answer. Okay, so let's mix these two things together, pyridine and HCl. So millimole amounts. This is 6 millimoles of pyridine. What is pyridine? A base, yeah, and I gave you the Kb. But this time you were titrating with HCl. So this is still a neutralization reaction. And I think this is 3 millimoles of H plus or HCl. Right? So after these two things neutralize one another, how much B do I have left? in my after line? How much B do I have left? 3. But remember, we added HCl, so we're neutralizing that base in becoming Hb+. So how much Hb+ do I make? Also 3, yeah. And so that's my base to acid ratio, right? And so these numbers also go into your Henderson-Hasselbalch equation. So pH equals pKa plus log base over acid, but this time that base to acid ratio is just 1, so it cancels out. So we just need to put in our pKa there. So here, I give you the Kb. pKb is equal to 8.77. So does that mean that my pH is 8.77? Nope, because this is pKb. It's pKb, I want pKa, so I just need to subtract this from 14. So I get pKa is 5.25 or 23 or something like that. Right? And so yeah, so my pH here is just equal to pKa, 5.23, because that base to acid ratio is 1. Always start with millimole amounts of everything first to figure out what is in your beaker. All right. Here, 50 milliliters of acetic acid, 51 milliliters of sodium hydroxide. So this, I think this is 10 millimoles of acid. And then, what is this? 10.2 millimoles of base. What's my limiting reactant now? The acid. So let me just write this BCA table again. But put these numbers in and think about how we're going to calculate the pH. So I'm putting in these same numbers. All right. I have 10 millimoles of HA, 10.2 of hydroxide. And so my limiting reactant is my weak acid, so minus 10, plus 10. So after this neutralization, I have 0 acid, 0.2 millimoles of hydroxide, and then 10 millimoles of A minus. So I have these two things mixed together, hydroxide and A minus. A minus is what? A weak base. Hydroxide is a strong base. So which one do we care about? The strong base. So we can just ignore the contribution of the A minus and actually just get the pH from hydroxide. All right. So the concentration of hydroxide is 0.2 millimoles. So we still need to calculate the concentration. Divided by the total volume, so it's 101 milliliters. And then that equals something, I don't know. I think I get the pH is like 11.30. Real basic. Okay. I really like this exam question. What was the exam question I asked you guys? Which titration has the higher pH or something at different points, right? So I had like, okay, you have acid A and B, right? Where like HA has a Ka of like 10 to the negative 4, and then HX had a Ka of 10 to the negative 6. And I asked you at 0 milliliters of sodium hydroxide. Oh, and sorry, I don't have enough information. So it was like 50 milliliters of 0.1 molarity HA for both of those. All right, so at 0 milliliters of okay, at 0 milliliters of 0.1 molarity sodium hydroxide, I asked which substance has the higher pH. So ask yourself, at 0 milliliters of sodium hydroxide, what is in your beaker? Just acid. So really, I'm asking you which acid is more basic, or which acid is less acidic. And so which one is that? Acid B. Yeah, because its Ka is a smaller number, right? Okay, and then what was the next one? I asked which one has the higher pH at 50 milliliters of sodium hydroxide, right? Like, yes, you could have calculated all of them, but you didn't need to. You didn't need to. So at 50 milliliters of sodium hydroxide, what is the predominant species? Is it HA, or like, is it acid? No, it's the conjugate base. So we are looking at A minus and X minus because this is the equivalence point, right? So how do we calculate the pH of X minus and A minus? We use KB, don't we? Yeah, so the KB for A minus is 10 to the negative 10. The KB for X minus is what? 10 to the negative 8. Yes, okay. So I'm asking you which one's more basic. So which one's more basic? It is B, yep, because it has the larger KB. It's more basic. And then what was the last one? Do you remember in the exam? It was which one has the higher pH at 60 milliliters of sodium hydroxide? What is the predominant species to calculate the pH at 60 milliliters of sodium hydroxide? Where are we on the curve? Way past the equivalence point. So does actually the identity of the acid really matter? No, because what do we use to calculate pH? Just the excess hydroxide. So what was the answer for that one? They both have the same pH. Yeah, because they both have the same amount of excess hydroxide. So this question really required zero math. If you could figure out where you were on the titration curve, I tried to make it kind of obvious, like that you were at the beginning, the equivalence point, and past the equivalence point. Yeah. Okay. Yeah, so what's the rule? Yeah, so the question is, oh, can't we just look at the Kas? Yes, you can. Because what's the rule? The stronger the acid, the weaker the base. So that means Ka for A is a strong acid, stronger or weak acid, so its conjugate is fairly not a good base. Versus B has a really crappy acid character, so it's going to have better base. Yeah, you can do that too. Or me, I like to look at the numbers, and because the numbers tell you the exact same story as well. Yeah. Okay. All right, so that's that. All right. Okay, let's do this last one. Calculate the pH when we mix this crap together. Okay, so HCl, so that looks like it's 10 millimoles of HCl. And look, we have 51 and 0.2 again. So this is what, 10.2 millimoles of calcium hydroxide. Oh, so is this the same as the previous one? No. Oh, actually, we never answered this one. This 32. But if you're clever and look at 31, is there anything special about 32? See how the volumes are exactly the same? So we are actually mixing, what is this, 10 millimoles of acid, but this time it's HCl, and we're mixing 10.2 millimoles of sodium hydroxide. So where are we on our titration curve? Way past it, yep. So how do we calculate the pH? Just excess hydroxide. So isn't our pH going to be exactly the same as the previous one? Yes, it is, because our excess is 0.2 again, millimoles over 101 milliliters. So we actually get the exact same pH, 11.3. Whether it's a strong acid or a weak acid, it doesn't matter, because the way we calculate pH is what is the strong base in excess. So just like before, that example I just showed where I had like a weak acid and a stronger weak acid, both of them have the same pH way past the equivalence point. So same, that's what 31 and 32 are trying to say too. And so 33, similar, I'm trying to trick you here, is question 33 also going to have a pH of 11.3? No, why? 2 hydroxides, yes. So we are actually somewhere else on that titration curve. So if I have 10.2 millimoles of calcium hydroxide, I actually have 20.4 millimoles of hydroxide. So I like to rewrite it that way because I can clearly see the 1-to-1 ratio. So how much hydroxide is left over? What's in excess? 10.4 millimoles is what's in excess after it neutralizes 10 millimoles of acid. And so over the total volume, 101 milliliters, and so you get the concentration of hydroxide afterwards is 0.103, and you get a pH of 13.013. So it is very basic. Very, very basic. All right, so that's the only difference. I tried to show you in 31 and 32, your pHs are the same because we're past the equivalence point and we have the same millimole amounts of acid and base in both of these, even though one's a strong acid and one's a weak acid. But for 33, the difference here is that the strong base is calcium hydroxide. So we actually get twice as much millimoles of base. So we're actually somewhere else on that titration curve, right? And I think I had an exam question kind of like this too, where I had you mix acid and like calcium or magnesium hydroxide, and a lot of students forgot to double the hydroxide concentration before doing the neutralization. So, pointing that out. Calcium hydroxide is different than sodium hydroxide. All right. Dang, we're almost done. Okay, so order the following substances in order of increasing molar solubility. So this is KSP. We like KSP. KSP is stuff dissolving in water. So we need to think about how these ions split up in water, and we can write their K expressions. But the nice thing about KSPs is there's never anything in the denominator. So when AB, so AB2 breaks up into solution, you get an A cation, but then you get 2 B anions. So if we wrote out an ice table for this, all right, if we wrote out an ice table for this, we would write, okay, I throw in some solid. I consume some of the solid, some of it dissolves. I gain an X amount of my A cation, but how much B anion do I gain? 2X. So at equilibrium, I have X amount of A, 2X amount of B. And so like always, the E line is what goes into the K expression. So the KSP expression in this case is still products over reactants. So KSP is equal to A concentration times B concentration, but it's squared because of the coefficient. So don't forget that back from chapter 15. And now once you have your K expression, this is where you put your X values in. So A concentration is X, B concentration is 2X, but that whole thing is squared. So KSP is equal to 4X cubed. And so what this question is asking, molar solubility, it's asking you to solve for X in all of these. So we can't actually just look at the values of KSP. We actually have to solve for X to compare how much these things, the extent they dissolve in water. So this KSP is equal to 4X cubed. Without writing the ice table, do you think we can get this one, A, B3? So when this dissolves in water, you will get X amount of A, but how much B do you get? 3X, yes. So when you plug this into the KSP expression, this is your A concentration. This one's your B concentration, but it has to be cubed because of that superscript or that subscript would propagate itself into a coefficient, right? So what's 3 cubed? 27. Okay, 27x to the 4th. So you solve for x. All right, what about this one? A little bit harder. So A 2B3. So you dissolve this in water, you're going to get 2A cations, and you're going to get 2x A cations, 3x B anions. So when you write the K expression, you get 2x, but squared. And then you get your 3x, but it is cubed. And so what is that? That's 4x squared. That's 27x cubed. What is that? Is that 108? Okay, 108x to the 5th, yes. And so you solve for x in all of these. And, oh, I said order them in increasing molar solubility. So I think if you calculate these, for A, X is 10 to the negative 5. B, it's 10 to the negative 3. And then C is 10 to the negative 4. So we see that B is actually the most soluble. Okay, so this one's the most soluble. And then A is the least soluble, based upon the X values, right? And so you would be wrong if you just looked at the K values, because A is least soluble, but it actually, C has a smaller KSP, and the reason is because the X expression for KSP is different for A and B because the stoichiometry is different. So we can't just look at the values of K. We have to actually solve for X. Okay, all right. Oh, geez. Okay, we'll be done here. But I want to actually let's just do finish this page. Because I said so, and I wrote the exam, so. Okay. The KSP of aluminum hydroxide is very small. So what does that mean about aluminum hydroxide? Is it very soluble in water? You put a chunk of aluminum hydroxide in water. Yeah, it's not a lot of it's gonna dissolve because KSP is really small. But the KF of this aluminum hydroxide complex is very large. Metal complexes are typically very soluble in water. So let's indicate whether the statements are true or false. Adding aluminum 3+ to a saturated solution of aluminum hydroxide will make the solid more soluble. True or false? False, yes, because you think about it, aluminum hydroxide, all right? This is its KSP expression, Al3+ plus 3 hydroxides. So if I have solid already in solution, and I add aluminum 3+, think Le Chatelier's principle. Which way does the reaction go? To the reactant. So you actually form more solid. So it actually becomes less soluble when you add more aluminum 3+, not more soluble. Okay. Adding hydroxide to a saturated solution of aluminum hydroxide will make the solid more soluble. You might think, yeah, so let me write the previous one was false. B, on the other hand, you might be following the same logic. Oh yeah, you add hydroxide, it pushes the reaction this way, and it becomes solid. But what piece of information in here did we not use yet? This aluminum complex is actually really soluble. So this one's actually a trick question. So this one actually is true because this is where you start to make the complex. So this is where KF starts to take over. All right, so that one's a trick question. Okay, so the reasoning for A and B are not the same. You would think if this thing didn't form a complex, then yes, adding hydroxide would make it less soluble. But because this is a special complex that is highly soluble with added hydroxide, yeah, KF takes over. All right, last one. Adding H+ to a saturated solution of aluminum hydroxide will make the solid more soluble. True. Why? Why? It what? It eats, yes, H plus eats what? OH minus. So if it eats that up, you're consuming it, you're removing it from the reaction, and so it shifts. Yeah, yeah, that's why the crunchy moms, they clean stuff with vinegar and lemon juice because it dissolves stuff. Yeah. Oh, because I gave you KF. And see how this KF has more hydroxides in it? Yeah. It forms more hydroxides. Yep. Yeah. Okay. All right, let's just do this last one and then we'll be done. Okay, predict the spontaneity of this endothermic decomposition reaction. Wow, I give you nothing here. Is this reaction spontaneous at high temperature, low temperature, never spontaneous, always spontaneous? So, I'll give you a hint. This is the equation we're going to use. Delta G equals delta H minus T delta S. Spontaneous reactions have what kind of delta G? Negative. So it doesn't seem like I gave you a lot of information here, but I actually did. Do you know the sign of delta H? Yep, it's positive. Because I say it's endothermic. How do we get delta S? We look at it. Yep. So what's the sign of delta S? Positive. Okay, now tell me, when is this reaction spontaneous? High temperature, low temperature, never, always? High temperature, yes. So this is how I like to do it. Temperature, Kelvin, all right? It's only ever going to be 0 Kelvin or any positive number. So when temperature is small, whoops, delta S will be small. So if delta minus T delta S, if that's small, this whole thing is actually positive when T is small. So we don't want that. We want spontaneous. So if delta T is big, right, we'll make it real big. Temperature is high. Now is this negative? If I have a positive number minus a big positive number? Yes, now it is, now delta G is negative when T is big because it makes the positive delta S very big. See how like a little positive number minus a big positive number. And that's negative. And so this tells us that this reaction is spontaneous at high temperatures. Yeah, so the answer is, yeah, spontaneous at high temperatures. Okay, yeah, is that it? Cool. Actually, can we just do the last one? Unless you really got somewhere to go, you can leave. But there's literally one question left. I just want to do it. Because this is a very much like on your own question. Consider this reaction, that goes to that. Using the provided data, calculate delta G for this reaction at this temperature when these are our partial pressures. So, delta G, that's like delta H and delta S. Like, is it products minus reactants? Look at this delta D. Sometimes there's a not on it, sometimes there's not. Did I make a mistake here? Like, no, that's deliberate. There's no not. So does that mean we can just use table values? No, not really. Okay, we can't. But we can in a little bit, in a sense, all right? So let's think about, this is a very much on your own question. When we use table values and there's a not, right? If it was delta G not, we would just do like products minus reactants, right? But what does that not symbolize? Standard conditions. What else do I give you here? Non-standard conditions. Yeah, so to me, I recognize we need to use that Q equation. All right, so if we look at the scratch paper here, we're actually using this equation. All right, delta G. See that this is the only equation where I have delta G without the not. This is delta G at non-standard conditions. It's not a mistake. So that means I need to figure out what delta G is, delta G not, and I need to figure out what Q is. And then I can get delta G. So let's go back at this. So I can kind of see where I get Q. Q comes from those concentrations. The hard part is, well, how do I get delta G naught? So this is my goal, minus RT, or is it plus RT ln Q? All right. So Q is actually going to come from the concentration. But I want to do the hard one first. Let's do delta G naught. So you would think, oh yeah, now I can use table values, products minus reactants. But did I give you delta G's? No, I didn't. I didn't. So, but can I use this information to get that? Yeah, there's another equation I can use. I can use, oh, delta G equals delta H minus T delta S. Can I get these values? Yes, those ones I can get from table values. Those are products minus reactants. So let me just highlight these. So these yellow ones are my products. This pink one is my reactant. So for all of these, I'm going to multiply 3 of my reactants because that's how the stoichiometry is. And then this hydrogen is times 2. So it's the yellows minus the pinks. So that means that delta H for this reaction is equal to negative 103.85 plus hydrogen, but it's 0, minus negative, or 3 times negative 74.8. So that's delta H of the reaction. Delta S of the reaction, same deal. It's products minus reactants, so 269.9 plus 2 times 130.58 minus 3 times 186.3. Right? So we need a products minus reactants for delta H and delta S first. So I get that delta H for this reaction is equal to positive 120.55 kilojoules per mole. And then delta S of my reaction is equal to negative 27.84 joule Kelvin. So these two pieces of information I'm going to put into my delta G. Because I didn't give you products and reactants for delta G. I only gave you delta S and, or I only gave you delta H and entropies. Okay, so at this point, since I have delta H and delta S for my reaction, I could technically calculate delta G at any temperature, but we're just working at 298. So we can just plug in 298 here. So delta G for this reaction is 120.55 kilojoules minus the temperature, 298, times entropy, but do make sure that the unit, they match, so it needs to be in kilojoules, so negative 0.02784 kilojoules per Kelvin. And so we get that delta G of this reaction is positive 128.8 kilojoules. Okay, but this is at standard conditions. This is if we did products minus reactants with delta G values if I gave them to you. Is that what we want? Do we want delta G naught? No, we need delta G without the naught. So we need to incorporate Q now with the actual concentrations that are given. So we can go ahead and calculate Q. Q is equal to products over reactants. So again, since gases are always referenced to ATMs, we can go ahead and just keep everything in pressures. So pressure of C2H8 times pressure, partial pressure of H2, that's squared, over partial pressure of CH4, and that is cubed. So now we put in those numbers. So C3H8 is 1 ATM. Hydrogen is 0.5 ATM, but it's squared. And then methane is 2 ATM, but it's cubed. So we see here that Q is equal to 0.03125. All right, and so now that we have Q and delta G naught, we can plug that into our original delta G equation, delta naught, where we do in fact incorporate Q. So just copy that. All right, so putting in those numbers, and then we'll finally be done. I should really have that in joules. So delta G naught is 128.8 times 10 to the 3 joules, plus R, so 8.314, 298, and then natural log of that Q I just got, 0.03125. All right, so we got delta G naught, we got that Q, plug all of those things in, and then we do get delta G for this reaction is positive 120.2 kilojoules, or whatever, I keep it in joules. 120.2 times 10 to the 3 joules for this reaction, given these actual conditions. So delta G is still positive, so even at these pressures, this reaction is still not spontaneous, all right? So this is definitely a harder question because I didn't give you a lot of information and we had to do some finagling to get there. So we went over the whole packet, so best of luck, everyone. I'm gonna stop recording so I can post this before I leave.